Abstractions play a crucial role in simplifying complex designs during formal verification. In certain scenarios, after reset, a design might have to wait for an array to initialize or a register to assume a specific value before a property's precondition becomes true. By eliminating unnecessary clocks and initializing the target array or the target register with relevant values immediately after reset, you can reduce the length of your counterexample significantly. When dealing with properties that take hours to reach the next bound, initial value abstractions can be really helpful in deciding whether you will encounter a bug within that bound or not. Let me tell you how to implement initial value abstractions in your designs. Feel free to reach out to me if you'd like to know further details on this or have any questions. To recap, up to this point, we have explored three fundamental techniques for reducing the complexity, along with one intermediate approach. Today, we'll delve into a second approach in the intermediate category itself, which is initial value abstractions. Additionally, I'll touch upon the concept of reset abstractions later in this video. Initial value abstractions allow any signal to take any value out of reset, regardless of what value the RTL is driving it to. Why do we need this? The primary goal is to reduce the length of counterexamples and identify the bugs more efficiently and quicker. Here is how you can achieve initial value abstraction. You can use a combination of abstract and assume commands. These commands are specific to certain industry leading tools, so you might need to find relevant commands in the tool that you're using. The abstract command specifies which signal you want to abstract, and the assume command adds constraints on the values that the signal can take after reset. Here I'm assuming a value 1 on the first cycle after reset. It's it's important to note that from the cycle 2 onwards, the abstracted signal will be driven by the RTL itself and not your abstraction. So whatever you need to do needs to be done in the cycle 1 in this case. There are two major phases of formal in a formal trace. One will be reset analysis phase and another will be formal analysis phase, which comes after the reset analysis. The command which I mentioned here, it works for signals that are not reset in the formal analysis phase, but only in the reset analysis phase. If there are some signals which are not falling in this category, which are getting reset in the formal analysis also, then you'll need a different approach for doing initial abstractions. Let's see that towards the end of the session again. Let's look at an example. Let's say we are verifying a cache, and specifically the cache hits. Let's see how a property that checks whether the cache will give a hit for a lookup or not. Let's say we are interested in the lookup to a symbolic address in the cache. I have already discussed the concept of symbolic variables, so I'm assuming you know them already. So let's say there is a lookup that matches the entry to the data stored in the symbolic address. So this will lead to this signal, this particular signal, cache matches lookup info, go high. In that case, cache should report a hit after say 5 clock cycles. This 5 is a random number that I chose. It will vary based on the design. The cache is designed in such a way that it will not have any valid entries out of reset. So all these will be invalid entries. Hence, every time you run this particular check, you need to first wait for 6 cycles. Again, 6, 1, and 5 in this case are all or random numbers that I'm choosing just for explaining this concept. So, like I said, every time you run this particular property, you need to wait for first 6 cycles to fill the design into the specific location. In this case, the location specified by the symbolic address. Then it needs to wait for a lookup to come. Let's say it takes a clock. Then it will check if the data present in the symbolic address matches the lookup criteria or not. If it matches, it should report a hit in 5 clock cycles. So in total, we have 6 plus 1 plus 5 equal to 12 clock cycles for this counterexamples, assuming there is a bug in the design and hit is not getting reported. So do we really need to wait for 6 clock cycle to fill for the design to fill a valid entry into the cache? Not really. What if we could get rid of this 6 clock cycles? So you will quickly get a counterexample which will uncover the same bug. That's what we are going to do with initial value abstractions. Here's how you can do it. You can use a combination of these two commands, abstract and assume, to achieve this. The first command, abstract, says that tells which signal you want to abstract. It's the cache entry, which is cache entry corresponding to the symbolic address. The second command, assume, puts a restriction on the data that this particular entry can take. In this particular case, I'm saying that after one cycle after out of reset, you can fill any data, but just follow this rule. The parity of the data should be 0. That means simply means XOR should give 0, one take be 0. Now, all of a sudden, you'll start getting counterexamples with just 6 clock cycles. So that's the beauty of initial value abstractions. You're saving all the time for doing the fill. You're filling the relevant data that you're interested in. Of course, the legal data specified by your constraints. And then when a lookup comes, which is matching the data that got filled, then it should look up. It should give a hit after 5 clock cycles. So from cycle 2 onwards, this particular cache symbolic address, it will be driven by the RTL itself. But for this property, we don't really care about that. So you save time, you save money. Is that all about initial abstractions? No. There is one small point that you need to be careful about, which I mentioned in the beginning. There's a special case where you need to be careful while doing initial abstractions. It is a case where the abstraction is done on signals that are getting reset after the reset phase. So in this particular counter example, these are 2 clock cycles. So reset analysis after happens for 2 clock cycles. After that, everything is called formal analysis phase. There is a special case where the signal to abstract is getting reset even one cycle after the reset analysis is over, as indicated by this red arrow. In these cases, you need to use dash reset value instead of dash init value while you do the abstraction. Other than that, the assume command remains the same. I hope you really enjoyed learning initial value abstractions. Try it out if you're dealing with cases where you're waiting for some kind of initializations in your failure traces. Let me know how it goes. I hope your checks reaches higher bounds and you find some really interesting corner case bugs. Thanks a lot again for watching. Make sure to subscribe to our channel and never miss an update. Stay tuned for our next video where we will cover another interesting formal verification topic. See you next time. Take care. Bye.